Welcome. Today we're diving into the fascinating world of oxidation and reduction, often referred to together as redox reactions. These processes are at the heart of countless chemical changes, from rusting iron to the way our bodies generate energy. Understanding redox reactions helps us make sense of both everyday phenomena and advanced scientific concepts. In this video, we'll break down what oxidation and reduction really mean, explore how electrons are transferred, and see why these reactions are so important in chemistry and beyond. Let's start by defining the basics before moving into real-world examples and deeper explanations. Oxidation is a term you might have heard in various contexts, but in chemistry it has a specific meaning. Oxidation originally referred to reactions involving oxygen, like when iron rusts. However, the definition has expanded. Now, oxidation means the loss of electrons by an atom, ion, or molecule. When a substance loses electrons, it's said to be oxidized. This process is crucial in many chemical reactions, including those that power batteries and even the metabolism in our bodies. Let's look at how this works in a simple chemical equation. Reduction is the counterpart to oxidation. While oxidation involves losing electrons, reduction is all about gaining them. When a substance gains electrons, it is reduced. This might sound a bit counterintuitive, but think of it as reducing the positive charge by adding negatively charged electrons. Reduction is just as important as oxidation and often occurs simultaneously in chemical reactions. Together, these processes drive everything from photosynthesis in plants to the functioning of electronic devices. Redox reactions are chemical processes where oxidation and reduction happen together. In every redox reaction, one substance loses electrons, is oxidized, and another gains those electrons, is reduced. This transfer of electrons is what makes redox reactions so dynamic and vital in chemistry. Whether it's burning fuel, rusting metal, or the reactions inside a battery, redox is at play. Let's explore how these reactions are represented in chemical equations and why they matter. The heart of every redox reaction is the movement of electrons from one substance to another. This electron transfer is what defines oxidation and reduction. When an atom or molecule loses electrons, those electrons don't just disappear. They're picked up by another atom or molecule. This exchange is fundamental to how energy is transferred and transformed in chemical systems. Understanding electron transfer helps us grasp why redox reactions are so powerful and widespread. Every redox reaction, there are two key players, the oxidizing agent and the reducing agent. The oxidizing agent is the substance that accepts electrons and gets reduced, while the reducing agent donates electrons and gets oxidized. These agents are essential for the reaction to occur. For example, in the reaction between hydrogen and oxygen to form water, oxygen acts as the oxidizing agent, and hydrogen is the reducing agent. Recognizing these roles helps us predict and understand chemical changes. One of the most familiar examples of a redox reaction is the rusting of iron. When iron is exposed to oxygen and moisture, it reacts to form iron oxide or rust. In this process, iron atoms lose electrons, are oxidized, and oxygen molecules gain those electrons, are reduced. This everyday phenomenon is a classic demonstration of how redox reactions shape the world around us, affecting everything from bridges to bicycles. Batteries are another great example of redox reactions in action. Inside a battery, chemical reactions transfer electrons from one material to another, creating an electric current. The part of the battery where oxidation occurs is called the anode, and the part where reduction happens is the cathode. This flow of electrons powers everything from flashlights to smartphones. Understanding the redox processes inside batteries helps us appreciate how these everyday devices work. Photosynthesis, the process plants use to make food, is driven by redox reactions. During photosynthesis, water molecules are oxidized, losing electrons, while carbon dioxide is reduced, gaining electrons to form glucose. This complex series of redox reactions captures energy from sunlight and stores it in chemical bonds. Without redox, life as we know it wouldn't exist, since plants are the foundation of most food chains. Just as plants use redox reactions to make food, animals and humans use redox to release energy from food. Cellular respiration is a series of redox reactions where glucose is oxidized and oxygen is reduced, producing energy, water, and carbon dioxide. This process takes place in our cells and is essential for life. By understanding the redox reactions in respiration, we can see how our bodies convert food into usable energy. Redox reactions aren't just important in nature, they're vital in industry too. Processes like metal extraction, bleaching, and even wastewater treatment rely on redox chemistry. For example, extracting metals from ores often involves reducing metal ions to pure metal. Understanding redox allows industries to develop more efficient and environmentally friendly processes, making it a key concept in modern technology. You might be surprised at how often redox reactions occur in daily life. From using bleach to clean stains to the way our bodies process food, redox is everywhere. Even the browning of fruit and the combustion of fuels in cars are examples of redox at work. Recognizing these reactions helps us understand and control the world around us more effectively. Keep track of electrons in redox reactions. Chemists use oxidation numbers. These are assigned to atoms in molecules or ions to indicate their degree of oxidation or reduction. By comparing oxidation numbers before and after a reaction, we can see which atoms have gained or lost electrons. This system helps us balance redox equations and predict reaction outcomes. Balancing redox equations is a crucial skill in chemistry. Since electrons are transferred, we need to make sure the number of electrons lost equals the number gained. This often involves splitting the reaction into two half reactions, one for oxidation and one for reduction, and then combining them so the electrons cancel out. Mastering this technique ensures our chemical equations accurately represent what's happening. Half reaction shows either the oxidation or reduction part of a redox reaction. By writing out each half separately, we can clearly see which species is losing electrons and which is gaining them. This approach makes it easier to balance complex redox reactions and understand the flow of electrons. Let's look at an example to see how half reactions work in practice. Handy way to remember oxidation and reduction is the phrase, Leo the lion says GER. Leo stands for lose electrons equals oxidation, and GER stands for gain electrons equals reduction. This simple mnemonic helps students and scientists alike keep the definitions straight, especially when working through tricky redox problems. Substances are especially good at accepting electrons and acting as oxidizing agents. Common examples include oxygen, chlorine, and hydrogen peroxide. These chemicals are widely used in industry and everyday life, from disinfecting water to bleaching fabrics. Knowing which substances are strong oxidizers helps us predict and control chemical reactions. On the flip side, reducing agents are substances that readily donate electrons. Examples include hydrogen gas, carbon, and certain metals like zinc. These agents are crucial in processes like metal extraction and chemical manufacturing. Understanding which substances act as reducing agents helps chemists design effective reactions and industrial processes. Bleaching is a common process that relies on redox chemistry. When you use bleach to remove stains, the active ingredient, often sodium hypochlorite, acts as an oxidizing agent. It reacts with colored compounds in stains, oxidizing them and making them colorless. This practical application of redox reactions is found in households and industries worldwide. Water treatment plants use redox reactions to purify drinking water. Chemicals like chlorine or ozone are added to oxidize harmful contaminants, making the water safe to drink. These redox processes are vital for public health and demonstrate how chemistry solves real-world problems on a large scale. Combustion or burning is a classic example of a redox reaction. When fuels like wood or gasoline burn, they react with oxygen, releasing energy, carbon dioxide, and water. The fuel is oxidized and oxygen is reduced. This process powers engines, heats homes, and even drives natural wildfires. Combustion shows how redox reactions can release large amounts of energy. Corrosion, like rusting, is a destructive redox process that affects metals. Over time, metals exposed to moisture and oxygen can corrode, weakening structures and causing economic loss. Preventing corrosion often involves protective coatings or sacrificial anodes, which are more easily oxidized than the protected metal. Understanding redox helps engineers design better protection strategies. Electrochemical cells, like batteries and fuel cells, harness redox reactions to generate electricity. These devices separate oxidation and reduction into different compartments, allowing electrons to flow through an external circuit. This flow of electrons is what powers our gadgets and vehicles. Electrochemical cells are a practical application of redox chemistry and technology. Galvanic cell is a type of electrochemical cell that generates electricity from spontaneous redox reactions. It consists of two electrodes, an anode and a cathode, connected by a wire and a salt bridge. As electrons flow from the anode to the cathode, electrical energy is produced. Galvanic cells are the basis for many common batteries. Electrolysis is the reverse of a galvanic cell. Instead of generating electricity, it uses electrical energy to drive non-spontaneous redox reactions. Electrolysis is used to split water into hydrogen and oxygen or to purify metals. This process is essential in industries that produce chemicals and materials we use every day. Redox reactions play a big role in food chemistry. The browning of apples, the fermentation of bread, and even the preservation of food involve oxidation and reduction. By controlling redox processes, food scientists can improve flavor, texture, and shelf life. This shows how redox chemistry impacts what we eat every day. Medical science uses redox reactions in many ways. For example, certain drugs work by oxidizing or reducing molecules in the body. Antioxidants found in many foods help protect our cells from oxidative damage. Understanding redox helps doctors and researchers develop better treatments and improve health outcomes. Antioxidants are substances that prevent or slow damage to cells caused by oxidation. They work by donating electrons to free radicals, neutralizing them before they can harm our bodies. This protective effect is why antioxidants are important in nutrition and health. Redox chemistry explains how these molecules keep us healthy. Environmental scientists use redox reactions to understand and address pollution. For example, redox processes help break down contaminants in soil and water. By studying these reactions, scientists can develop better ways to clean up the environment and protect ecosystems. Redox reactions are at the core of modern energy storage solutions. Rechargeable batteries, like those in electric cars, rely on reversible redox reactions to store and release energy. Advances in redox chemistry are helping create more efficient and longer-lasting batteries, which are crucial for renewable energy technologies. Redox flow batteries are a special type of battery that uses liquid electrolytes to store energy. These batteries can be scaled up easily, making them ideal for large-scale energy storage like balancing power grids. Their operation is based entirely on redox reactions, making them a promising technology for the future. Metallurgy, the science of extracting metals from ores, relies heavily on redox reactions. For example, iron is extracted from its ore by reducing iron oxide with carbon. This process removes oxygen from the ore, leaving behind pure metal. Understanding redox is essential for producing metals used in construction, electronics, and transportation. Redox reactions also play a role in agriculture. Soil chemistry, fertilizer effectiveness, and even plant health are influenced by redox processes. For example, the availability of nutrients like nitrogen and iron depends on their oxidation states. Farmers and scientists use this knowledge to improve crop yields and soil quality. The Earth's atmosphere is shaped by redox reactions. Processes like the formation of ozone, the breakdown of pollutants, and even the cycling of carbon and nitrogen all involve oxidation and reduction. These reactions help maintain the balance of gases that support life on our planet. Brilliant colors and explosions of fireworks are the result of redox reactions. Different metal salts are oxidized or reduced during combustion, producing vivid colors and spectacular effects. Understanding the chemistry behind fireworks adds a new layer of appreciation to these dazzling displays. Art conservators use redox chemistry to restore and preserve valuable artworks. By carefully controlling oxidation and reduction, they can remove tarnish from metals, reverse discoloration, and protect paintings from further damage. This blend of science and art ensures that cultural treasures last for generations. Space missions rely on redox reactions for life support, energy, and propulsion. For example, fuel cells that power spacecraft use redox chemistry to generate electricity from hydrogen and oxygen. Understanding redox is crucial for developing technologies that allow humans to explore and survive in space. Redox reactions are used to control pollution in air and water. For example, catalytic converters in cars use redox chemistry to convert harmful gases into less toxic substances. These technologies help reduce emissions and protect the environment, showing the practical benefits of understanding redox. Modern electronics, from smartphones to solar panels, depend on redox reactions. The movement of electrons in circuits and the operation of semiconductors are all governed by redox principles. Advances in redox chemistry are driving innovation in electronic devices and renewable energy. Many color changes in chemistry are due to redox reactions. For example, indicators used in titrations change color when they are oxidized or reduced. These visual cues help chemists monitor reactions and determine when a process is complete. Traditional photography relies on redox reactions to develop images. Light-sensitive chemicals are oxidized or reduced when exposed to light and developing agents, creating the final photograph. This fascinating application of redox chemistry has captured memories for generations. Many cleaning products work through redox reactions. For example, hydrogen peroxide and bleach oxidize stains and kill bacteria. These products are effective because they alter the chemical structure of unwanted substances, making them easier to remove. Redox reactions are vital for human health. Our bodies use them to generate energy, fight infections, and repair tissues. Imbalances in redox processes can lead to diseases, making it important for doctors and researchers to understand and monitor these reactions. Natural cycles like the carbon and nitrogen cycles depend on redox reactions. These cycles move essential elements through the environment, supporting life on Earth. For example, bacteria in soil use redox reactions to convert nitrogen into forms plants can use. This interconnected web of redox processes keeps ecosystems balanced. Wrap up: oxidation and reduction. Redox reactions are fundamental to chemistry and life itself. From powering our devices and bodies to shaping the environment and driving industry, redox processes are everywhere. By understanding how electrons move and how substances interact, we gain insight into the workings of the world. Whether you're a student, scientist, or just curious, knowing about redox opens up a deeper appreciation for the science all around us.